Plastics are ubiquitous in our modern society. Chances are, from where you're seated now, you can reach several different items that contain plastic. The very device that you're using to watch this video likely contains plastic. Plastics are so useful because A, we can readily produce a wide variety of different plastics from simple organic precursors, and B, we can also vary the properties of that plastic just by slightly modifying our original organic molecule. Now, these plastics are all made, or at least most of them are made, using free radical reactions. So again, we talked about the free radical reaction previously. It allows us to get unique reactivity because of the high reactivity of those free radical compounds. So in this video, we're going to look at how we can use those free radicals in order to make plastics, and we'll also look at some applications to other organic reactions as well. Our plastic polymerization or formation reaction begins with initiation, as with all of our other free radical reactions. Now, initiation, of course, requires a homolytic bond cleavage, so we usually want to see a purely covalent bond so that we have an equal sharing of electrons, and it's easier to split those electrons as opposed to that heterolytic cleavage where one of our atoms is taking all those electrons. So with our plastics, we generally use some variety of peroxide. A peroxide is a compound where we have two oxygens bonded together with a single bond. So this is our most common hydrogen peroxide, where we just have our two oxygens and then two hydrogens on either end. Now, hydrogen peroxide, of course, our oxygens will equally share those electrons, and so then we can break it apart with our homolytic bond cleavage and form two units of our radical here that will then react to form our polymer. Once we've formed our initial free radical in our plastic polymerization, we of course can proceed with our propagation step, as with our previous free radical reactions. So our propagation begins with our free radical that we produced in our initiation, and it's going to react with our organic unit that we're using to build our polymer. So polymers are made from many units of our smaller organic molecule that are built together to make this very large molecule that gives us the unique properties of our polymer. So here I'm going to use ethylene or ethene. So this is our smallest alkene with our two carbons double bonded together. So ethene or ethylene, when it's reacted together into a plastic, makes polyethylene. Right? So we're taking many units of our ethene, combining them together, and making this polyethylene plastic. Polyethylene, of course, is one of our most common plastics. It's found in plastic bags and a variety of other different plastic compounds as well. So our free radical, of course, is going to attack here. And in this case, of course, as we've seen with our alkenes, that alkene double bond is always the most reactive spot. So it's going to be using its electrons to bond with our free radical. So one electron, of course, comes up and pairs with the unpaired electron of our free radical, and the other electron will go over to one of our other carbons. So as usual, of course, after this first step, we've created now a new bond between our old radical and our ethene in this case, and we've also created a new radical. So here we have our initial product. This is now a new alkyl radical essentially. And of course what we saw before is that alkyl radical could then react with another non-radical compound and continue this propagation chain reaction. Now, when we're making our polymer, what we're going to do is we're going to add a very small amount of our radical catalyst, our peroxide, right? So the peroxide is not really here to make our polymer, it's just here to make that free radical that gets our reaction started. So we're going to have a very small amount of this acting as our catalyst essentially, and a very large amount of our alkene here that we're going to be building into our long polymer. So when we have this free radical, this alkyl radical that's produced, the most likely thing for this to react with is actually another unit of our alkene here. So we bring in a second unit of our alkene since we have, again, a very large concentration of our alkene. And again, we're going to do the same thing that we just did. Right? So we take that electron, we attack our double bond, which acts as our most reactive site in our alkene, and we dump an extra electron out to our carbon to make another alkyl radical. So after this step, we end up with, so still our peroxide oxygen attached. We have now this guy attached to another carbon down here. That's our new bond that just formed from these two radicals reacting. And we have another carbon up here that has a new free radical. Now, again, of course, this free radical here, the most likely thing for it to run into is another unit of our alkene. So I can again draw out my alkene and show my free radical coming in and my alkene giving electrons from the double bond, and of course taking one electron again to make a new free radical. So now our product is going to be our oxygen, got our first two carbons from our original unit, our second two carbons from the second unit that we added on, and now a third set of two carbons from our new carbon that we just added on. So in each step, we're just adding on another two carbons from our initial monomer, our alkene monomer, we refer to it, and that's producing our large plastic polymer. Right, so we just keep adding this on. You can see our three individual units here, unit 1, 2, and 3. And again, that can continue as long as our chain reaction of our propagation goes on. So this can go on for hundreds or even thousands of steps, and we can produce a very large chain of our carbons. Now, of course, if we want to vary what our plastic looks like, we can simply remove these hydrogens here. And if we use a more complicated alkene, let's say, so one example, we could take our alkene and then add on a aromatic ring here. So this is our arene that we looked at earlier in the semester. So we've got this double bonded cyclic system. And this is what we call styrene. And so when this reacts together, we would make polystyrene. We'd just be using the same double bond to polymerize, right? Extend that chain reaction for multiple steps, but we're just changing what else is attached to our monomer as well. Right? So then we'd have our rings sticking up here off of our carbons in addition to the two carbon units that are getting polymerized in our chain. Right, so we're adding on these units each time as we extend our chain. So the polymerization process of our plastic will continue until, of course, we hit that termination step. So our chain will build up over and over again. Eventually we'll get to the point where our chain will stop as we hit another radical. Right, so we can represent this as follows. So we have our 2-carbon repeating unit of our polyethylene, and we can put this in brackets and put a little n here, indicating that this is going to repeat some number of times based on how long we keep our propagation step going. And then we'll have 1 unit at the end that will have our free radical. And of course, our chain reaction stops when that free radical hits another free radical, resulting in a termination step. So maybe we run into another unit of our original peroxide free radical. So if we run into another unit of that, we would combine these 2 radical unpaired electrons, and we end up producing our polymer chain, where we have repeating units of those 2 carbon units from ethylene, or of course if we're using styrene, we'd have our polystyrene with these repeating units of our styrene molecule. And then we end up with another free radical attached at the end of our from our peroxide. So we have n repeating units, and we end up with these oxygens at either end from our free radical of the peroxide. So the end result, of course, is this very long plastic chain. And we can have some control over the length of it just based on how much of our catalyst we add, how long we kind of allow this propagation step to continue this chain reaction and keep adding on units of our individual monomers here. And again, so that can allow us to create a wide variety of different plastics. The second reaction that we'll look at here is an anti-Markovnikov addition of HBr to alkenes. So again, you're going to be looking at alkenes as our main functional group that's reacting with our free radical. But here, instead of reacting multiple alkenes together to make a long polymer, we're just going to be adding on hydrogen bromide. Now, of course, as we've seen before, we can add hydrogen halides like hydrogen bromide to alkenes, just adding that and allowing the nucleophilic addition reaction to take place. However, those will normally follow Markovnikov's rule, where we're always adding our nucleophile on to the more substitute position. In a free radical reaction, we're going to manipulate the normal selectivity to allow an anti-Markovnikov addition, where our bromine is going to be going to the less substituted position. As with our plastic polymerization, our reaction is going to begin with some form of peroxide. I'm showing hydrogen peroxide again here, although we could have other peroxide as well, with perhaps other carbon groups attached on here. Our peroxide, of course, has that oxygen-oxygen single bond, which can break apart in our homolytic bond cleavage in order to give us our 2 peroxide free radicals. So we get these 2 hydroxide radicals, and then these, of course, will be reacting in our propagation step. Propagation, of course, will begin with our free radical. So we're bringing in that hydroxide radical. This is going to react with our hydrogen halide, our HBr. So we bring in our single electron. As always, the free radical initiates the reaction. And then we're going to take one of the electrons from our bond here. Of course, the bromine is more electronegative, so it's going to take the other electron, and will form our bromine radical. So as always in our propagation, we start with a free radical, we react with a non-radical, and we produce a new free radical. So we produce a new bromide radical, and of course we're just producing water here from our peroxide. So we'll have some water produced here. Now our bromine radical is going to react with our alkene. In this case, I'm going to use propene here, so our 3-carbon alkene, although of course this could be any alkene we want. As always, our free radical is going to be reacting with that alkene double bond, since that's the most reactive point of our alkene. So we give one electron here to make our new bond to the bromine, and the other electron, of course, is going to go to one of our adjacent carbons. Now remember, when we talked about free radical stability previously, we saw that substitution of our carbon will affect that free radical stability. So our electron could go to either of these carbons. One of these carbons is a primary carbon. It only has one attached carbon, while the other carbon is secondary. Our free radical, of course, will want to go to the more substituted carbon because that will make the more stable free radical intermediate. Right? The more stable our intermediate is, the smaller our activation energy barrier is, and the faster our reaction will proceed. So our free radical goes to the more substituted carbon. Now when our free radical goes to the more substituted carbon, that means, of course, that our bromine is bonding to the less substituted carbon. Right? So the bromine ends up over here, bonded at that less substituted carbon, while the free radical comes up here on the more substituted carbon. Now, of course, you should note here already, our bromine is now in the anti-Markovnikov position, right? Bonded to that less substituted position. Whereas if we had done this using just the normal addition of HBr to our alkene, we would have our carbocation intermediate at the more substitute position, and then we'd have the bromine adding on there as well. Now our propagation step needs to continue here. We still have a free radical, so we're going to react this now with another unit of HBr. Again, of course, our free radical attacks that bond. We give the extra electron to our bromine, so we end up with a bromide radical. And our alkyl halide, which acts as our major product here. Right? So we added on our hydrogen here using that free radical, and this will be our primary product. As always, of course, our major product forms during the propagation step, because this is the step that's going to be repeated over and over again to produce a large quantity of that particular product. Right? So this bromide radical here can go back and react with the second unit of our alkene and produce more of our free radical, or of our alkyl halide product rather. As always, our free radical reaction will conclude with a termination or multiple termination events. Right? So again, we could have our peroxide radicals running into each other to create our hydrogen peroxide. We could also have our bromine radicals combining to form diatomic bromine. Or we could have our alkyl radical combining with a bromine radical or a peroxide radical to create a dihalide. Now it's important to remember here that all of these are minor products, right, because they're only produced by this relatively rare event of two radicals coming together and combining to form different products. So there are many different possible termination products, but they're all going to be relatively minor. Whereas our primary products will be these products that we're forming during our propagation step. So our alkyl halide, and of course we're producing some water here as well. Those will be the products that we'll produce in the most majority. So what we see here are examples of free radical reactions with now alkenes to produce some very useful products. Right? Through our anti-Markovny combination, we can add on hydrogen halides, but now to that last substitute position, allowing us to create a new group of alkyl halides. With our polymerization reaction, of course, we can create a wide range of incredibly useful plastics. We can carefully change the properties of those plastics based on the structure of our monomer. So again, we're seeing how free radicals, although they can be dangerous because they're high reactivity, are very useful for creating different organic compounds for us.